Hello everyone, my name is Hani Sami. I'm gonna present our recent work for building FScaler, an intelligent agent utilizing reinforcement learning for horizontally scaling resources inside fog clusters. This work was done in collaboration with Dr. Azzam Murad, Dr. Hadi Otrok, and Dr. Jamal bin Tahir. In one of our previous work, we proposed an architecture for building on-demand fog clusters for dynamic fog creation. On-demand fog formation utilizes any type of volunteering computing resources for hosting microservices in a form of containers next to users. These fogs are managed inside a cluster by a Kubernetes orchestrator. We then formulated the problem of container placement in the on-demand fog clusters. The problem was to select fogs and assign the proper services to them based on multiple contradicting objectives. This problem was solved using an evolutionary mimetic algorithm. Now, after containers inside the clusters are placed, demands for services can increase or disappear over time. For this reason, we need a solution that can horizontally scale the fog application resources based on the changing demands while also taking into consideration the changing resources on fogs. The outline of this presentation, first I will go over the literature work and then over the proposed architecture. This is followed by a brief overview of the MDP formulation. I will then show the SARSA algorithm used for building FScaler, and then we'll present the dataset and experiment evaluation. Finally, I will conclude with some future work. For the related work, this is the first paper that proposes on-demand fog formation. The second one is publishes the idea of container placement problem and how it's being solved using evolutionary mimetic algorithm. Furthermore, this work in 2019 proposed scaling resources in the fog environment using reinforcement learning. However, their main limitation is to do the scaling inside one fog only. Another work was proposed by the same authors recently for scaling services on multiple fogs. However, they used heuristics to do the placement of newly scaled services. In our work, our solution considers scaling in a cluster managed by an orchestrator. We let the agent do the placement intelligently, and we consider changing resources of fogs inside the cluster. In this work, we use FScaler based on reinforcement learning to do the scaling. Our solution guarantees the ability of load balancing the demands on different fogs after doing the scaling. The agent is able to add and remove containers based on changing demands in a single decision, while specifying the fogs to add or remove containers from. The challenge we faced is that our policy is stochastic because of the changing demands of the users and the changing resources on fogs. In our proposed architecture, we show to the left in the yellow box two fogs forming one cluster. The state of the cluster is changing from t-1 to t. We can also see a representation of the reserved resources in gray, utilized resources by FScaler in red, and free resources in green. The demands coming from the user on the left are studied by the Kubernetes master of the cluster shown in the blue box to the right. Inside the Kubernetes master, we integrate our FScaler where learning and decision making happens using reinforcement learning. Now the MDP formulation. In order to solve our problem using reinforcement learning, we need to build an MDP containing states, actions, cost function. Obviously, our probability matrix, transition matrix is unknown because of the changing demands of the users. So we use these components to build our state and action spaces. P is the list of containers to be placed, each having CPU, memory, and disk requirements. H contains a list of hosts, each having CPU, memory, disk requirements, and distance from the user. UT is the experience response time by the user at time t. MT is the scaling and placement decision at time t taken by FScaler agent. Mmax will be used to form our action space. It has a list of maximum number of containers that can be placed on each fog. RT contains the list of available resources on each fog at time t. Now, the state of our MTP formulation contains UT, MT, and RT. The action space can be minus Mmax plus Mmax, which means I can remove Mmax containers from fogs, or I can add up to Mmax containers to a fog. The cost function, we have 3 sub-cost functions, and each one is multiplied by a weight lambda, and this weight will be varied between 0 and 1, where the sum of all the weights will be 1. These weights can be adjusted in order to give importance to some objectives over the other. Now this figure shows the evolution of the components through time. At the beginning of time step t, action at AT is taken. From AT, we can conclude the placement decision MT. The agent then waits until observing UT and RT, which are used for calculating CT, the cost function at time t, and moving to state ST. This process then repeats for the next time steps. Now, the 3 cost functions are the response time, the response time cost, the resource cost, and the distance cost. Now, for the response cost, it measures how much the response time decreases after doing the scaling decision. The resource cost measures if FScaler did a scaling decision that surpasses the available resources for any fog. Distance cost ensures that scaled instances are placed close to the original fog and therefore close to users to avoid networking delays. The end goal is to minimize the cost function, and more details about the calculation are provided in the paper. Now, in order to build FScaler, our probability transition function is unknown. Thus, for this work, we use a model-free on-policy reinforcement learning algorithm named SARSA. More details about the algorithm is provided in the paper. Now, in the experiment part, we used WSDream for getting real response times experienced by users requesting a given service. We also used Google Cluster Trace 2011 version 2 dataset to get the list of resources required for 2 study services for 2 different scenarios. These are the parameters used for each scenario, where we also varied the weights for each of the 3 subcost functions. Now, these are the convergence results of the 2 scenarios, and then we can show how the cost evolves over time and decrease at the end and converges to a certain value. Now, in the first figure, we show how the response time improves from 2.4 to converge to 1.5 on average. In the 3 other figures to the right, we show the changing available resources for each fog over time after taking the FScaler decisions. A negative value means services placed surpasses the amount of available resources, and 0 means that all fog's resources were used. For the first fog, almost the full resources were used, which is shown in the second figure, because of its proximity to the user. We can also observe that the resources utilization of fogs converges over time. This shows that our FScaler agent is able to generate optimal decisions. In this work, we provided an intelligent solution for scaling fog application horizontally. We integrated FScaler in Kubernetes master in a novel architecture. We modeled FScaler as MVP and provided a solution to our problem using SARSA, reinforcement learning algorithm. And then we experimented with the real data set and showed the improvement achieved when using FScaler. As one of our main future work, we will be using reinforcement learning approximation solutions to achieve a more scalable version of FScaler. This is because when the input grows, the state and action spaces will grow. Therefore, a tabular solution will not be practical. Thank you.